Hello, good morning students. Today I am going to teach you a new topic, that is root locus technique. Root locus technique says only whether system is stable or not. It doesn't give complete information about stability of the system or instability of the system or marginally stable of the system. It doesn't give complete information, but only raw stability analysis only it gives whether system is stable or not. It doesn't give complete information as root locus technique gives. Okay, so today this is a very important topic, root locus technique. I may take around 5 lectures to complete this root locus technique. Okay, the first we see that here the learning objectives. So at the end of this unit, you will be able to study the basic properties of root locus, and second thing is you are able to sketch the root locus using these properties. So there are 9 properties, there are 9 rules. Okay, so first we study about these 9 rules, and after that with the help of these 9 rules we are going to construct the root locus. Okay, so next we see that here root locus techniques. See, the root locus technique was introduced by W.R. Evans in 1984 for the analysis of control system. Okay, so root locus basically it was introduced for the analysis of control systems. Okay, and also see that the root locus technique is a powerful tool for adjusting the location of the closed loop poles to achieve the desired system performance by varying one or more system performance. So this is a very important tool for adjusting the location of closed loop poles to achieve the desired performance by varying one or more system parameters. You see it here, so we can adjust here closed loop poles, okay, by varying k value from 0 to infinity, so that it will achieve desired system response. Okay, so we have seen in raw stability criterion, right? So your response, so this is our response, this is a response. There are 4 type of responses. We have undamped response, underdamped response, and a critically damped, overdamped response, right? So mostly this underdamped response is mostly accepted response in the industry. It means more control systems have underdamped response nature. Most of the control system in industry, in industrial control systems, right? So here the closed loop poles we can vary, right? So it means we can adjust the closed loop poles by varying the system gain. So as system gain you are varying, so what happened, the location of the poles will be adjusted so that it will give the desired performance of the system, right? So we see here some important of root locus, right? This root locus technique is an important tool in designing control system with a desired performance. So this root locus technique is useful for designing control systems with a desired performance. Okay, and the second thing, this desired performance of the system can be achieved by adjusting the location of its closed loop poles in the S-plane by varying one or more system parameters. This already I have explained to you. Okay, so and also the root locus technique is also used for stability analysis. The root locus technique is also used for stability analysis. Okay, and using a root locus, the range of values of k for a stable system can be determined. Okay, so it is easier to study the relative stability of the system from the knowledge of closed loop poles. So this is the very important points we have to understand. The main important thing is I already explained, by just adjusting the closed loop poles. All right, so you can get the desired response of the system by varying one or more system parameters. Okay, so that's the important things you should remember. So I'm going to explain this with one example. What is root locus method? What is root locus plot? I'm going to explain you with one example. So what is root locus? What is root locus? What is the root locus plot? Right. So if you take any closed loop system, right? So this is a closed loop system. I'm going to take, right? So k by s plus 1, okay, and s plus 2, s plus 1, s plus 2, and this is CFS. So this is your error detector, this is the plus, and here is the negative feedback. This is a unity feedback you are using, right? So this is R of S, and this is E of S. This is the E of S. Here K is system gain. Here K is system. Here K is a system gain. Here you see here this is a open loop system. This is open loop system. K by s plus 1 into s plus 2 is a open loop system. Now when you connect this, the unity feedback system, so it become a closed loop system. Here we are interested to study stability of closed loop system, right? So here the closed loop poles of the system is equal to closed loop characteristic equation of the system. Okay, so here a closed loop, this closed loop poles means 1 plus gs into hs. Okay, the closed loop poles of the system is equal to characteristic equation of the system. Characteristic equation of the system. See here closed loop poles, closed loop poles same as a open loop poles. Closed loop poles here same as open loop poles, but here we are interested to find stability of the closed loop system. So now what I'm going to do, then when you make it, this is a your transfer function. So transfer function here, if you take this one is CFS by, or transfer function CFS by R of S is equal to CFS by R of S is equal to what will come. So you know the equation, that is G of S by 1 plus G of S into H of S. 1 plus G of S into H of S. What is G of S? Here G of S is equal to K by S into S plus, S plus 1 into S plus 2 by 1 plus K by S plus 1 into S plus 2 into 1. Right. So when we divide it, you will get So k by s plus 1 into s plus 2 by 1 plus k by s plus 1 into s plus 1 into 1. So what you get? Finally you will get c of s by r of s is equal to, so you will get k by, okay, s square plus 3s plus 2 plus k. So this is the closed loop system. This is the closed loop system. Now you take characteristic equation. This is the characteristic equation. Characteristic equation is equal to what? S square plus 3s plus 2 plus k is equal to 0. So just to find the roots for this equation. When you find the roots for the equation, you can write here s1, s2. The roots are minus 3 by 2 plus or minus 1 by 2 root 1 minus 4k, root minus 1 minus 4k. How do the system will behave for k values? So how does this is the roots of characteristic equation. Okay, now I am going to change the value k values from 0 to infinity. So how these roots will move in the s plane. Okay, you just see that I'm going to take as a, this is a first when k is equal to 0. When k is equal to 0, so what are the roots when k is equal to 0? So when you put k is equal to 0, so you will get, so your s1 comma s2 is equal to minus 3 by 2 plus or minus 1 by 2, plus or minus 1 by 2. It means what are the roots now here? Minus 3 by 2 plus 1 by 2. So that is one root. S1 is equal to minus 3 by 2 plus 1 by 2. So you will get 2 minus 2 is equal to minus 1. And another root. So minus 3 by 2 minus 1 by 2. So you will get minus 4 by 2. So you will get two roots. What are the two roots? Minus 1 and minus 2. So when k is equal to 0, so you got s1 is equal to minus 1 and s2 is equal to minus 2. Okay, this when k is equal to 0, it means you will get the open loop poles. You will get the open loop poles. You see that this equation, this is the equation. So s is equal to minus 1, s is equal to minus 2. Okay, you got this equation. So now I'm going to draw I'm going to locate these poles on the s plane. So you just see that here. I'm going to locate, or I can locate here the poles here. So this one is the s plane. This is the s plane. So this is a sigma. So this is a j omega, right? This is a minus sigma. This is minus j omega. So this is s plane. This is the s plane. Okay. So when k is equal to 0, whatever poles, so s is equal to minus 1 and s is equal to minus 2. If you just see, this one is the minus 1 and this one is the minus 2. So your poles are located where? Your poles are located at k is equal to 0, minus 1 and minus 2. Okay. So now the closed loop poles are same as the open loop poles here. See, closed loop poles are same as the open loop poles, right? This is the closed loop. From the closed loop I have taken characteristic equation. When k is equal to 0, so what happened? The closed loop poles are same as the open loop poles. Okay. Now in the second I am going to take k is equal to 1 by 4. So what do you get when you take the k is equal to 1 by 4? When you take the k is equal to 1 by 4, so what you get? When you get k is equal to 1 by 4 in the second case, in your equation, So your equation is, so s1, okay, comma, your equation is s1 comma s2 is equal to, so your equation is minus 3 by 2, okay, plus or minus 1 by 2, 1 minus 4k. So this is our characteristic equation. In the second case, when k is equal to 1 by 4, when you put k is equal to 1 by 4 in this equation, so what happened? This become 1. So 1 minus 1, 0, 0 into 1 by 2, 0. So you will get, so your roots are repeated and real. So what happened? It means s1 comma s2 is equal to minus 3 by 2, minus 3 by 2. It means your roots are real and repeated. When roots are real and repeated, so what happened? Your system critically damped. Your system is critically damped. Okay. So in the last case, when k is equal to 0, it means your roots are real and unequal. So in that particular case, so your system is over damped. So now what happened here? Roots are real and equal. So your system is, so it's critically damped. Okay. So I'm going to look at the roots here, minus 3 by 2. So here minus 3 by 2 means minus 1.5, minus 1.5. So here roots are real and equal. So you just see that when k increases, when k is equal to 1 by 4, so what happens? This root will move this direction and this root will move this direction. So this root here is over the k value minus 1.5. So at minus 1.5, the roots are meeting at minus 1.5. So it means it's critically damped. Okay. If you further increase the k value, what happens is these roots will break away. So this will root will break away, and the root will go one this direction, another one will go this direction. You see that as k value increases, first k is equal to 0. Alright, k is equal to 0 means open loop, closed loop poles same as the open loop poles. So when k is equal to 1 by 4, what happens? This root will move this direction and this root will move this direction. Or I will take a big sheet and I will explain to you. So if we just take here, if we just take here the big sheet. So here if you take the root, if you take the S plane, this is a S plane, this is, we call it a S plane, this is a sigma, this is a minus j omega, this is, sorry, this is plus j omega, minus j omega, this is minus sigma. Okay, in the whatever roots, so first this one is the 0, here is the minus 1, I am going to put here is the minus 2. In the first case, in the when k is equal to 0, so your poles are remaining at here. Okay, when k is equal to 1 by 4, what happened? When k is equal to 1 by 4, so your roots moved, one is this direction and another pole is moved at this in this direction. So when k is equal to 4, it means this value is a k is equal to k is equal to 1 by 4, and k is equal to 1 by 4. So you got your roots are minus 1.5. Okay, that means k is equal to 1 by 4, your roots are real and repeated, it means critically damped. If we increase the further k value, what happens? Your roots become complex conjugate. It means, so in this case, you just see that in this case, this is the second case. Okay, when I am going to increase k is equal to, means I increase the k more than 1.4. If you increase the k value more than 1.4 in the third case, so your system become, so your roots become complex conjugate, and your response would be underdamped. So when you further increase, the roots become complex conjugate. The roots become complex conjugate. Thus you see here in the picture here. So if we further increase here, k value, so it will break away, and one root move this direction, another will root move this direction. Okay, so it will terminate at, if we still increase, so it will go this. Okay, this will go this direction. So it means it's a terminate at k is equal to infinity. Okay, and here also terminate at k is equal to infinity. So what happened, we just observe here. In the first case, when k is equal to 0, the roots are here. One is s is equal to minus 1, s is equal to minus 2. So when k is equal to 1 by 4, so what happened, your roots are equal and real. So what happened, so you will get your system will give critically damped response. It means at k is equal to 1 by 2, these two poles moving, one pole is moving this direction, another pole is moving this direction. When at k is equal to 1, so what happened, so they meet at this point, and if further increase, so if k value, further increase k value, so what happened, this will go this direction, the roots become complex conjugate. It means it will give underdamped response. Okay, here k is a running parameter. Okay, so a root locus plot is a complete description of the system with respect to specific parameter of the design. Okay, you see that here, this is very important to understand. So k is equal to 0 here, so k is equal to 0. So when it is started here, k is equal to 0, the poles are here. As k is increasing, what happened, this roots become real and equal. Right. So after that, open a further increase the k value, so the this will break away, and this root move this direction. If we just see that there are two poles here. There are two poles. Okay, so s is equal to minus 1 and s is equal to minus 2. So since there are two poles, there are two root locus branches. So one root may go this direction and another will go this direction and terminate at k is equal to infinity. So one root starts at k is equal to minus 1 and it will go and terminate at k is equal to minus infinity, and another root will start from k as minus 2 and terminate at k is equal to infinity. So it's possible this root may go this direction or go this direction, or this root may come this direction. Okay, so number of poles is equal to here number of root locus branches. Okay, so the here so the plot the root locus with respect to k, which varies from 0 to infinity. Okay, total behave. So now we take a open loop transfer function. So that is g of s. This is g of s. Okay, but this is open loop transfer function. So now I'm going to make it as a closed loop transfer function. So now I'm going to take a unity feedback control system. So this is g of s. Okay, and I'm going to connect unity feedback system, that is h of s. Okay, so this is our error detector, and this is negative feedback. This is input r of s, and this is output is your c of s. So what is the transfer function here? C of s by r of s is equal to, so g of s by 1 plus g of s into h of s. Okay, so now what I'm going to do, if I break this loop here, if I break this loop, it means here So what you get, here is R of s. Okay, when you break the loop, so what happened, this will become a output. Okay, so in that case, so I am going to write g of s into h of s. You will get g of s into h of s, the transfer function. So that is, we call it open loop transfer function. Open loop transfer function. Open loop transfer function. Okay, here the characteristic equation of the system becomes 1 plus gs into hs is equal to 0. So here 1 plus gs into hs is equal to 0 is the characteristic equation of the system. So where gs into hs is open loop transfer function. So this one here 1 plus gs and hs is equal to 0 is a characteristic equation. Okay, here I am interested in the roots of the characteristic equation because the roots of this characteristic equation are nothing but closed loop poles of the system. So they are going to give transient behavior of the system. So you got right here. So here, so I am interested only here the closed loop poles. This means the roots of the characteristic equation. Okay, so these roots of characteristic equation will give the transient behavior of the system. So when you take a open loop, so when you take this open loop, now I am going to take open loop. So open loop transfer function, so that is g of s into h of s, that is g of s into h of s. So I am going to write k, so this is a pi j I is equal to 1 to m s plus z I by pi j is equal to 1 here. So n, j is equal to 1 to n s plus p p1. Okay, so here one thing we should understand here, see here the poles could be in the right half of the s plane. This means open loop poles may be in the right half of the s plane. Okay, what is the system condition to the systems to be stable? So all the poles should lie on the left half of the s plane. So here your open loop poles may be lying on the right half of the s plane. Okay, but what happened, may have unstable open loop system. Unstable open loop system means the poles may lie on the right half of the s plane, but a closed loop system, what happened, it makes the unstable open loop system stable system. So now I am going to write this, I am going to write as a f of s. I am going to write this as a f of s. It means g of s and h of s I am going to write as a f of s. So now characteristic equation of the system become, now characteristic equation of the system become 1 plus fs is equal to 0. 1 plus fs is equal to 0. It means, so here f of s is equal to what? F of s is equal to minus 1. F of s is equal to minus 1. Now what I am going to do, I am going to scan for the entire state space. So I am going to scan this. So this is a sigma minus sigma j omega. So this is minus j omega. So now what I am to do, I am going to scan for the entire state space and sigma and j omega to find out those points 1 plus fs is equal to 0, and join these points, it is called root locus. Okay, so now what I am going to do, f of s is equal to, here we already know, minus 1. When you take a magnitude of this, so you will get minus 1. So e is equal to minus f of s 1. So when you take a magnitude, so that is f of s, when you take a magnitude, so it become 1. It become 1. So then you take the angle condition. It means f of s. So this is called angle condition. Angle condition. Angle condition. So angle f of s is equal to odd multiple of 180. 2q plus 1 is the odd multiple of 180. So this is called the odd multiple of 180 degrees. Okay, here the q is equal to 0, 1, 2, 3 and so on, right? So if we just take the graph, if we just take this graph, yeah, so this is S plane, j omega, this is S plane minus j omega, this is sigma plus sigma minus sigma plus j omega minus j omega. If you take any point on this, if you take a point here, yes, one point on this S plane, so any point on the root locus path is a point on the root locus path. So see, if there is a point is there, so if this point satisfies angle condition, magnitude condition and angle condition, we say that this point is on the root locus path, right? So now f of s, so now f of s is equal to, here I am taking as f of s. F of s, you know that k, right, sigma, so I is equal to 1 to m s plus zi by some j is equal to 1 by n s plus p I. Okay, so this k value here, k value is greater than 0 or less than infinity, greater than or equal to 0 or less than infinity, the k value. So when you take magnitude, condition for this, so it become 1. So we take the magnitude condition. So the magnitude condition is here, the magnitude condition. So f of s is equal to, so I'm going to take a magnitude, okay, k into pi I is equal to 1 to m s plus zi, okay, by pi j is equal to 1 to n s plus z pj. So when you take a magnitude for this, so it become k by s plus zi by, this is I, j is equal to 1 to n s plus pj. So this is equal to 1. If this is f of s is equal to 1, okay, this is called angle, this is called magnitude condition. So then what is the angle condition? Angle condition, so we say that here angle condition is pi I is equal to 1 to m, so s plus zi. So when you take this one upside, it become n j is equal to 1, so s plus p j, s plus pj. So this is one angle and this one is the another angle. So this is equal to plus or minus, okay, so tq plus 1 190, okay, this is an odd multiple of 190. So this is the magnitude condition, this is the magnitude condition,
This is angle condition. So if this point on the S plane point is satisfies magnitude condition, that is magnitude condition is equal to 1, and angle condition, this is a 180 of odd multiples. So if that is satisfies, so any point which satisfies this condition is on the root locus, right? If these conditions are satisfied, the point is on the root locus. So you can write any point which satisfies any point which satisfies these conditions. These conditions here, these conditions means here angle condition and magnitude condition. So these conditions is on the root locus path. So locus path. So we will check with one example. So the example, we take one equation here, that is with one example I am going to explain this. Okay, so k by s into s plus 1 into s plus 2 is equal to f of s. So what is the magnitude condition for this? Magnitude condition. What is the magnitude condition f of s? So f of s is equal to here, so k by s magnitude, s plus 1 magnitude, s plus 2 magnitude, right? So if this magnitude condition is equal to 1, okay, suppose you take this one, you take any point, this is a point, so this is the point name is given s naught, okay. So this point s naught is equal to sigma naught plus j omega naught. If I take this angle condition, that is s is equal to sigma naught plus j omega naught, okay. So this is a magnitude condition. So k by sigma, so this omega naught j, okay, into what is the magnitude here, sigma, in place of s you put sigma naught plus j omega naught, sigma naught plus j omega naught plus 1, okay. And another magnitude I am going to write here, sigma naught plus j omega naught plus 2. This is another magnitude. If this magnitude is equal to 1, so this angle condition is satisfied. Magnitude condition is satisfied. If f of sigma naught plus j omega is equal to 1, so so magnitude condition is satisfied. Then what the angle condition? How we can write the angle condition? Angle condition. So we can write like this: minus s angle minus s plus 1 angle minus s plus 2 angle is equal to odd multiple of 2q plus 1. So you put here s is equal to sigma naught plus omega naught. So if this angle condition is satisfies, if this point satisfies angle condition and the magnitude condition, we say that this point is on the root locus path, right? So how are we going to find the magnitude here? How are we going to find the magnitude? So if you just see that this is a point, right? This is a s naught and you've taken point here. So what are your roots? S is equal to 0 1 root, and s is equal to minus 1 1 root, and s is equal to minus 2 1 root. You just draw a vector from here for this point, another vector you draw, another vector you draw, okay, right? And what is the angle for this? What is the angle for this? If you take angle like this is angle theta 1, this is angle theta 2, this is angle theta 3. so you can measure easily these magnitudes. So this magnitude, so here magnitude you can measure with the scale, you can write numerical value, and from this s is equal to -1, from here to here we can also measure this magnitude and substitute here, and this magnitude we can measure and substitute here. So k value may be some value, if you just divide it, it should get 1. So if 1 you get, so angle condition is satisfied. Okay, then what is the angle condition? So angle condition here, theta 1 minus theta 2 minus theta 3 is equal to odd multiple of 2q plus 1. If these two conditions satisfied, this point is on the root locus. And also I can take one more point also. Here also I can take one more point. So that is S1. S1 means here sigma 1 plus omega 1 j. Like this it will go. If after following the same position, if this point is satisfied, so the point is on the root locus path. Again I can take another path. So that is a S2. If S2 also satisfied angle condition and magnitude condition, that point is on the root locus. So you can draw a line. So this entire line, so what are the points are in the root locus, that satisfies the root locus. It means the points are satisfied angle condition and magnitude condition.